Hi everybody, I'm David Pius, and we are starting today this Bayesian machine learning sessions. Today, basically, we're going to do we're going to talk about the logistics, and we're going to do a very brief introduction to one simple model to understand the basic concepts, right? So, so these are the motivations. So we are finishing this year at ISM at the Exeter, so that's a sort of way to leave some legacy for the future. Then we have at CSIC this AIHUB connection, which focuses on artificial intelligence, and there's been a number of discussions within the various meetings that we have done, and well, there were a bunch of people who were interested in Bayesian methods, so that's a second motivation. Then in the consulting that we do with other institutes or the corporations that we do, again, several people have shown interest in Bayesian methods. So third reason. Then, well, CSIC has a bunch of statistical courses, but they are kind of oldie. So that's one way to modernize a little bit the institution. And finally, for some of the people in our group and some of our sponsors also need this kind of polishing. So I guess these are a few good reasons. The idea is that well, we start from like an overview of Bayesian inference, which what is good from this is that it provides a unified and coherent approach to problems of interest in statistics, inference, and prediction, and decision support. And we'll explain a little bit on this, right? And hence,
I have to share the screen. I just realized we're.
Oh, sorry.
Just in case somebody's watching at some.
Sorry. Right. So, as I said, and as a consequence, it would provide support. I think this is quite important. It is a unified approach. So there's not a bunch of recipes, but it's a sort of a broad theory, and it's coherent in the sense that we shall see through these weeks. And as a consequence, you would expect that it would support most machine learning problems. But the thing is that, as we've been seeing, is that most of machine learning or mainstream machine, let's say mainstream machine learning focuses on maximum likelihood estimation or maybe maximum likelihood plus regularization. Let's say, the mainstream is this, which can be partly interpreted as Bayesian, but just partly. And the things are that in machine learning, things are changing slowly. For example, changing slowly in the sense that people are more interested in what is now called probabilistic machine learning. And there's two things that, standard machine learning, let's say, focuses on point estimations. But now there's some emphasis in some domains on more on predictive intervals, and also explainability is also a major thing. And one way to go through to it is through Bayesian methods. Okay, so that would be the focus, or that would be the reason. But the thing is that it leads to complex computational problems, as Simon knows well. And some of them need to be solved yet. So that's first point. So the idea is that we're going to make an intro to what is known and what is yet to be discovered. But on this journey, we're gonna introduce at the same time key Bayesian concepts, which are quite important and not so well known. As a sort of minor anecdote, I'm doing at the moment the National Statistics Institute exam. I mean, these are the people that are going to serve us as civil service in statistics. Almost nobody of the none of the candidates. I mean, they do well on the sort of, let's say, p-tests, sort of p-values and all this kind, but they do not do so well in I don't know, in these basic things. And also for the same price, we're gonna see key models in applications. Okay. So these are our objectives, key concepts, key computational methods, so case methods in problems, a Bayesian view on popular machine learning models, and a focus on R and stand for Bayesian computation. We'll make some pointers to Python, etc. if you want, but we have Simon. If you, I'll pass the questions to Simon if and the idea is that would be sort of what we aim to do. So an introduction, which basically will put the key concepts and key problems, and then we'll spend quite a bit on how do we perform computations, but I mean not just per se, but accompanied by problems. So basically, from a let's say historical point of view. We'll go through some approximate methods based on normality. Then we go through MCMC methods. Then something which is not frequently explained, which is how do we use this to support decisions. Then we'll go through large-scale computations, and then we'll do through a Bayesian machine learning as smorgasbord, right? So I put this 5 or 6, but if you're interested in other models, just tell us. That's the email address. So we chose to use these BART machines as an example of I mean as the Bayesian version of regression trees, regression and classification trees. Gaussian processes, neural nets, mixture models, Bayesian optimization, and variational autoencoders. So that's our initial plan, but we have time if you want other stuff for whatever reason, just let us know and see what we make them. So R and Stan and the slides images from the bibliography proposed. So that's the basic bibliography. For a first introduction, that would be probably a very good pointer, right? This is a sort of very popular point, but I think it's they're recording this. I think this is not such a good book, right? But it's very popular. The how do you say, the labs are good, are very good. The book is a bit complicated, and then. A bit confusing, I would say, but these other are examples of this new wave that I say of making machine learning in a Bayesian fashion, right? And so these are the sort of core references. And these are other complementary bibliography for various aspects. I don't know, from Bayesian optimization, more on regression, etc., etc. I like this a lot because this makes a sort of very let's say fair comparison between Bayesian and frequentist methods, and it's quite nice. And you have the slides if you want, and a bibliography on Bayesian and R. So these are like 3 sort of basic, let's call it basic books or the essentials. That's more complete and recent. And the stand manual it's full of examples. For the next time, I'll put some Python books if you prefer to do Python. So until May the 5th, we still have this machine learning thing running. So we have 2 more sessions. So we'll start at 12, and then after May the 12th, we'll start at 10. So that's the email. If you want to make questions, whatever, and we'll try to answer them. And the stuff that we prepared, the slides, the recordings, the labs, etc., we put it there. So talking about labs, so as like a first thing, we have this lab 0, which basically is a recording, reminder of key concepts in R, in case you don't know it. We shall try to make some kind of recordings associated with the lab, but I don't promise because we might do it, but we okay. Any questions? Because comments or somewhere online? Oh, there's 4. There's 4.
I don't think so. I think
is that from before?
We're there before, I think.
Okay, can see the screen. Blah blah blah. Okay, good. Thank you. So, the first, but now it doesn't work. This guy.
Oh, sorry. Yeah, I had to touch here. Right.
Okay, good. So the first session is which will be very brief today. It will be it's an introduction, right? So I mean, it will be brief today, but it will be for 2 more weeks. So we're gonna do the basic Bayesian inference concepts through simple but very fundamental models. So this is not basically not large scale yet. We can do, let's say, more or less the computations with pen and paper if you want. Or what I mean, the sort of the calculus required, you can do it with. Of course, when you do it with large data sets, you cannot do it by hand. But basically, the follow up you can do it with by pen. And the sort of models that we are going to show is first models on proportions through the beta binomial model. Then models on means through the normal model. These are like very classical. Then we'll do an introduction to Bayesian linear regression and hierarchical models. Then a very simple approach to logistic regression before moving into computations, and then dynamic linear models, which are quite important in forecasting, right? In time series models, right? So one thing is with this you have an idea. We'll have an idea on the key manipulations that we can do, and also they put us on the border to require computation. Let's say smart computational approaches would be the basic to move ahead into this more sort of recent or more trendy machine learning models. So then we'll do a recap, basically. Trying to do in a sort of general way what is based in inference, prediction, and decision making, and motivating computational issues. So today we just do this first chunk because it's our first day, and stuff you can get it from Hub and this other set of reference. Okay. And there's already a lab. Well, there will be there's a lab with this, a lab 1.1. So for chapter 1, the first lab, and this will include the exponential gamma model, which applications, for example, in reliability. We'll do. There's a lab on beta binomial, which is what we are doing today, and the kind of example is that we use is on fraud detections, you can use it in cybersecurity, etc. And there's a third model that it's next week, which is the normal model, and that's the typical application would be in ecology, right? I mean, the example, the little case study or made up case study that we have put is in ecology, right? Okay, so that's the plan for the next 3 weeks. And we're gonna start with this one, right? So first, some basic examples. The things that I put in red are quite important. So that's to make the sort of differentiation or with the emphasis on the sort of, let's say, new community on machine learning and what, so that's Chema and Simon, and the old style statisticians like Sonali and myself, right? She's not old, but she's an old style statistician, right? I'm old. So, and also it marks a difference between, let's say, what is more the typical working in, I mean, quite frequent work in for example, in biology, right? So in biology, a quite frequent thing is hypothesis testing, for example. And I would say that in machine learning, they don't care about hypothesis testing. So the sort of traditional problems in stats were point estimation. I mean, so for hardcore stats would be point estimation, interval estimation, and hypothesis testing. Point estimation is important in machine learning because, well, that's what they do, and but they use it. I mean, the problem they focus is on prediction. Now, I would claim that, at least for the kind of work that we like to do, this third bunch of problems on decision support is the most important, at least in an engineering environment, etc. So, I mean, we do stats and we do machine learning to support decisions. So that's the more, and the good thing is that everything can be viewed as in a unified view, from a unified point of view, and that's quite important, or quite interesting, I would say. So that's again the idea that we don't need to learn various recipes, but we have a unified point of view on these activities, so I think that's quite important. The second thing which is in red is this one. It's subjective, so we use probabilities, but the emphasis is going to be slightly different. The emphasis on frequencies or classical statistics is on concepts like on the frequencies approach to probabilities, and our emphasis is going to be on subjective probabilities. So I mean the numbers are going to use they all have the same mathematical properties, right? But in this case, the interpretation of these numbers is as a measure of the degree of belief that a given subject, that's why it's called subjective, in a given moment has about the occurrence of an event, right? So that's slightly different. Note that in particular, I mean, this as a sort of particular case, you were saying the degree or the degree of knowledge, the degree of belief that I could have no knowledge, and that I will reflect it with what we shall see are non-informative priors. So that's quite important. So that's quite important because in many problems they will have access to experts, scientists, etc., that have prior information, or we could have prior information for previous studies, or we could try to put some kind of a structural knowledge within the models that we use, and we can do it through the prior distribution. Right, so that's quite important. Yeah, that's very important. Some just notation, but we'll use this conditional probability notation that's not so important. That's the sort of you have to cut this and put it on your room, right? So that's the sort of rule that we shall be using to update information. So we'll move from prior probabilities to posterior probabilities. So probabilities before knowing why to probabilities before knowing why to probabilities after we know why, and that's Bayes' formula, right? We'll see that, which is a sort of, I think it's the most important formula in science. It's mathematically trivial, but it's the most important formula in science. And all the problems that we're going to see will come from, because this will be very complicated to compute, right? That's the evidence or the marginal of the data. Here I put it as in the discrete case, but this is normally an integral, right? I mean, in the continuous case would be like an integral, right? And this will be very complicated, and this will motivate all the sort of discussions that we shall have on. This will be even more complicated in very large dimensional problems, and that's why and that's the sort of major discussion at the moment in this domain. Right. So,
David?
Yeah.
I'm kind of perturbed by the notation because, you know, we think of probabilities as acting on sets.
As acting?
On sets. So what are X and Y?
For the moment, think that these are discrete variables, right? To simplify, right? And yeah. So X is an observation, right?
So just 1 point.
Yeah, just 1 point. Yeah, and Y is another one. Yeah. And if you want the probability over a set, right? So you just need to do the summation over the x's in that set if it's discrete and if it's continuous.
Yeah, but we tend to write sets with 1 point as the point with curly brackets around.
Yeah, well, you're a fundamental mathematician. I'm an engineer, so allow me.
Yeah, sure.
Yeah. Oh, we put an integral here. Okay, so that's a sort of initial notation, and actually this notation is because the most of the things that, well, many of the things that we're going to see here will be discrete. So that's the example that, and that's how we want to proceed. We are going to introduce models through examples or through cases. And that's the first one that we're going to. This is probably the simplest example. It's the beta binomial model. My little daughter, is, for example, studying the binomial model. So we make it a little bit more interesting by doing the beta binomial model to learn about the probabilities. But that's something that we learn in first year of bachillerato, baccalaureate. So that's we studied it, at least in Spain here. So that's the kind of problems that we consider. Consider a recovery protocol for an SME, a computer service, after a cyber attack. So assume that we have one protocol and we wish to assess it, typically to compare with another one. So we do these kind of things to make decisions, as I said. So, or maybe biologists do these kind of things for the pleasure of knowledge, etc. But in the end, what you do for pleasure, somebody maybe not yourself, but maybe somebody in 50 years or 70 years will use it for a new drug or for whatever recovery. So I'm a sort of shorter-sighted person. And we do this to compare with other protocols. So this guy is offering me this protocol. This other guy offering me this protocol. Which one do I use? Okay. So I used to do this when I was in charge of these kind of things at the university. So the kind of data that we get is, what we claim is this protocol has been tested in 12 attacks and it's been effective in nine occasions, right? And we have to be precise. We have to, I don't know, what is effective. We must be precise of what is effective. And effective, let's say, is, in this case, is that the attack duration was less than 1 hour, right? So in 1 hour, we were able to recover or get rid of this attack, right? Otherwise, we cannot go ahead or whatever we so. Okay, so the model is it's an easy one. It's a binomial model. As I said, my daughter is studying this, and she's 16 years old, I think. Yeah. So there's n trials, identical and independent. That's maybe. I mean, this is more. I mean, this is actually requiring quite a lot, but let's assume this. And there's two results. The protocol has been successful or ends up in a failure. And what we want to count is what we count is the number of successes in n trials. And the thing that we want to learn, the parameter that we want to learn is the success probability in a trial. Okay. And the model that the kind of model that we use is the binomial. In this case, would be a binomial with 12. It was before 12 trials and this probability. And if we have x equals 9, is that okay? No? So we use this. Well, I'm using that this is proportional to, well, there's been nine successes and 3 failures. So this is proportional to this. I don't care about this. There's a number here. I'm sorry. So this is 12 over 9, 12 choose 9, but I don't care about it. We don't care. And this is 1. Okay. So what? So first element, there is the likelihood, which summarizes the information about the data. Okay. And the first approach is we maximize likelihood, and that's the maximum likelihood estimator. We maximize this with these constraints. That's easy. That's in this case is 9 divided by 12. 9 number of successes divided by number of trials. If you do, it's quite simple. And basically, that's what we've been doing in the machine learning thing that is running in parallel at the moment. But this has several defects. In this example is very easy, but quite frequently it's not defined. We have one defect, for example, if we have 12 successes, the MLE would be 1, or if we have 0 successes, the MLE would be 0, and a few other things. One defect from a point of view is that also we could have some prior information about this, and we are not using that information. We have very valuable information, and we are not using it. And I put here an example. We could have another source of information. This is a sort of very vague information. This is somebody who has no information about this, right? And we can model in this way. There's other models, ways to model this, but let's use this prior. And then we update. The update in this case would be for Bayes formula. So it's the product of the prior and the likelihood. In this case, going back to you, this would be the density. In this case, that's a density, and this is the discrete probability, right? And well, you can do this. This is 1 times this. And you recognize this as a beta. This comes from a beta distribution with parameters 9 plus 1, 10, and 3 plus 1, which is 4, right? Okay. So several good things I shall be telling at the moment is there's the sequential nature of Bayes rules. So This would serve as a prior for the rest of the follow-up of the study. So I don't know, if we have in 5 applications 3 successes, so we'll have again what is the probability of theta 1 given that we have now 3 successes. So this is the prior, which is the previous posterior based on the likelihood in this case. This is proportional. Some numbers are, but we don't care about them for this discussion. And now this is the beta, which we recognize as a beta 13.6, right? But there could be, as I said, the previous prior was uniform prior. There could be another guy who knows more, and he could say something like, well, I think that the theta is around 80%. Bigger values are more likely. So we could model this. We'll see how to do it, but we could model this prior as a beta 4.1, and this would, after the first experience of first data, we updated to a beta 13.4, and then we to a beta 16.6, right? The same data. And again, another interesting thing is we put here the evolution of the distributions. So that these were the prior. So this was the first person, and this is the second person. So they are quite different, right? Now, after the first bunch of data, they start to look closer, and then they are super closer, right? So the idea is that we can, I mean, if the experts are not how do you say I mean, if they are flexible enough, right? You can see that there is a convergence on their learning. So the posteriors tend to converge, right? So we can talk about a phenomena of as data gets more and more abundant, there's a convergence in learning, or we can say that there's a consensus, and also there's some kind of asymptotic behavior which makes them converge. This doesn't happen always, right? This is a very simple model, the beta binomial, and it happens here, but there's some sort of complex problems, like for example in Dirichlet processes, etc., that this convergence does not happen. But under sort of pretty general conditions, this happens. So that's also good from the point of view of science, right? So basically, if the experts or if the people providing priors are not dogmatic and they process the information through Bayes' rule, then there's a convergence, so which is quite good. Okay. So now the thing is that the posterior summarizes all the information available, and then you can use it to all the typical things. For example, you could use a point estimate, right? So let's focus on this case, right? So this means we focus on right. No, we focus on this person at this stage, right? So this information summarizes this info and the data that we got, right? And then we can do point estimates. So for example, we could summarize it through the posterior mean, right? But why not, we could use, I don't know, the posterior median, or we could use the posterior mode, right? Which, by the way, is I mean, in machine learning, it's used a lot, it's the map thing, right? But we could use an internal estimate. So rather than focusing on this theta on a point estimate, we could use we could say like a probability, sorry, an interval with probability with a high, which contains the true value with a high probability. And that's also quite important because I mean that's a sort of major difference. We don't do these confidence interval things, but the information, the measure that is associated with intervals is probabilistic, which is much more meaningful, right? Yeah. Another typical problem would be hypothesis testing. So the question is the protocol effective? So we want to find out whether for example, whether the proportion of success is bigger than 0.5, right? And we can compute this probabilistically. So and again, we can respond to this type of hypothesis test in a probabilistic manner. Right, and that's a sort of interesting. These three questions are of interest in sciences, right? In engineering and in many other problems. I mean, this is not that important, right? Hypothesis testing is not that important, or interval estimation is not that important, and we focus more on forecasts. And again, the thing is that we can, in a unified manner, we can respond to these type of questions through the predictive distribution. So the predictive distribution is a computation that we shall be doing. So basically, what we can say is that if the type of argument or the computation is should we know the parameter, right? That would be the probability of having k successes, for example. I mean, the question that we want is how many successes shall we have, given that we had 9 successes in the. So we want to relate it with what Jesus mentioned before. This type of question is, what is the probability of more than 4 successes in the next 7 trials, knowing that we had 9 successes in the first 12 trials? So that's the question. The basic ingredient would be this one. So we need to know what is the probability of having k successes in 7 trials, given that we had 9 in 12 trials, right? So the kind of reasoning which will be repeated, and it's quite important to, is that should we know the true value of the parameter, the true probability or the actual probability, this would be the probability, right? The required probability. But we are uncertain about this theta 1, and the uncertainty is modeled through this posterior, right? What we do is we integrate out this uncertainty. We remove it by integration, by probabilistic computations. So we do this and this is, in this case, it's quite easy, and we get this is the number. And then to answer the question, we just need to do it for 5, 6, 7, and 7, and 6 and 7, and that would be the probability, right?
I'm still confused about the presentation. The first big X equals K.
Yeah. That
I understand. That's the set where X takes the value K.
Yeah.
But the little x, what's the meaning?
That's the data. That's the data we had. So the situation is, we did 12 experiments, and nine of them were successes. So we know that in 12, that's what it's trying to. That's what we are trying to say.
So yeah. X could be like the sample realization or something.
Yeah,
like
it's been there. Yeah. Okay. I admit that this is not the best notation. No. Yeah, I concede it to you. This one I concede it to you.
If I understand it, I'm happy.
Good. Yeah. Okay. So you could say, well, this is pretty high, right, or sufficiently high, and I add this computation, right? Observe that this we can still do. We have done this all by hand. We can still do by hand, but this is our life will. Now we said that we do these kind of things in the end to see if this protocol is better than another one, because there's this guy offering me. There's these 2 companies which are offering me their services. Should I trust, or should I hire each of them, or one of them, right? So to compare, assume that we have another one who has come and says that we've been successful in 6 opportunities out of 10 with the same definition as before. So one is Telefonica and the other one is my uncle's company, right? So I can the whole model. The whole model would be this is our earliest model. Well, our earliest model was this one, right? With this one, okay, with theta one, and the second model is the model referring to the second producer or is this one, right? So it's a binomial with theta with 10 opportunities and some property which some proportion that we need to learn, right? Now, a natural thing to find to try is to compare both of them. So we could try to find what is the probability of the first company being better than the second one. This probability is bigger than this one. Given that I know that there have been they have been successful. The first one has been successful in 9 out of 12 opportunities, and this one has been successful in 6 out of 10 opportunities. So it's the natural. This is a natural measure to do, right? So what is this probability? So if this probability is big, I think that theta 1 is better than theta 2, and I would hire them, right? Now, at this point, and we've been just like 20 or 30 minutes. At this point, we can no longer do it on these computations by hand, I think, right? And one very easy way is through simulation, and actually that's something that we're going to do repeatedly. So basically, what we do, we shall do is sample from let's say 1,000 observations from this, 1,000 observations from theta 2 from this distribution. We do the differences, right? And then we count how many of these are bigger than 0, and then we divide it by 1,000, and we have an estimate. We will do some more fancy things, etc. But that would be sort of a nice way to start. So in one experiment with this, 700 out of 1,772 theta 1s were bigger than the corresponding theta 2, right? So that's my estimate of the probability. I said we can refine this, but let's do it in a rough way because it's the first day and it's almost time for lunch, right? So what do you conclude in this case? So we said if this is big enough, let's say if this is bigger than 0.5, let's go for theta 1, right? So this is bigger than this is 0.7, which is bigger than much bigger than 0.5. So we heard theta 1. Everyone is happy? Yeah? No, you're
not paying attention.
Yeah, I know. So this is not a very good idea, I would say, because things cost, right? Yeah, it could be that this is better, right? Actually, it is more, the quality is better, but this could be very expensive, right? And we might not afford that, right? So we need to take this into account when making decisions, and that's one example, right? So we can consider the consequences when we succeed with the protocol and we do not succeed with the protocol. Suppose that this was A, the first distributor, and this is the second distributor, right? So imagine that this is cheaper than this one, right? So, and I'm putting here some numbers which are utilities that we'll talk a little bit later on, right? And in this case, the best utility is 1 and the worst utility is 0. So this is the worst situation. So we do not succeed and pay a lot. This is the best situation. We succeed with the protocol and we pay, it was cheap, right? For us to buy. And intermediates, so this is 0 point, which is worse than this, but it's better than this. So basically what we are saying is that we are more we weight better the quality than the cost. So this is the best, second best, third best, and fourth best, right? And then what we do is we could associate with to plan A the expected utility. So the probability of succeeding given the data times this utility plus the probability of not succeeding given this utility, and the same for plan B. If we do this, the expected utilities given the parameters would be in the first case like this, right? So it would be 0.8 times theta 1 plus 0 times, right? And in this case would be 1 times theta 2 plus 0.2 times this one, right? And if we take into account the uncertainty that we have about theta, so we end up with numbers which are, the expected utility of plan 1 is 4/7 and the expected utility of this one is 2/3. So 2/3 is better than 4/7, right? So the answer would change. Okay. So that's something that we try to. That's an idea that we will try to focus on a lot. That we use this to make decisions in biology, in medicine, in whatever, and we do these kind of things to either to help somebody make decisions or to make ourselves the decisions. Right. So a very quick recap of what we've learned. We've learned with an example this very important model. Right, so in this case, there was just one parameter, which is the parameter of the binomial, right? The probability of success, right? The model that we have is like this. So before we didn't put this number because we didn't care much about it, right? And this can be this distribution can go through 0 to n. We get some data, right? There could be several observations. Let's put it just like that. And the procedure is we go through, we model the likelihood, right? We get the likelihood. We typically log it, right? And then we maximize it. And in this case, we use the maximum likelihood, which is something like this. Okay. But as we say, this has a bunch of problems. In the sort of Bayesian approach, besides this information from the likelihood, right? We use prior information eventually available. It could be that there is no prior, well, there's no information, so we can use some kind of non-informative prior. And that was one example. We'll discuss about it. But sometimes we have more information and we would need to elicit, and we will go through this type of problems. But basically, in this case, a typical approach would be we assess a couple of quantiles of the prior, and then we, with some numerical analysis routine, we get the corresponding parameters. So. And then what we do is multiply, that's the posterior, which is proportional to the prior times likelihood, right? And in this case, it's quite easy because these are conjugate. So the prior has the same fractional form as the posterior. Well, we have the update is we move from a beta alpha beta to beta alpha plus x beta plus n minus x. So that's quite easy. So the posterior summarizes all the information. And then we can do, I mean, if you can think in parallel through simulation. So, but we can summarize it in a for example, through the posterior mean, right? Or through the posterior median, or through the posterior mode, or whatever. It depends. Actually, you can justify choosing this or this or this or others in terms of the type of loss that you use. And if you need to summarize it through an interval, you use a credible interval, an interval of posterior probability of the content that you want, and you can either do it symmetric interval, so you leave out the same probability both at the left and the right, or you could do another possibility would be to do a highest posterior density interval, and basically the left and the right extremes have the same density, and so you have to lower down this value until you reach the probability content that you want. Again, you can justify these or other types of intervals depending on the kind of loss function that you use. And again, quite important, you can compare this with the concept of confidence interval, but the good thing, I mean, this is kind of better because it has a sort of coherent interpretation. Hypothesis testing, again, we base the hypothesis tests in the posterior, right? Sort of, I mean, you can think sort of in a unified way. For example, I mean, you could have three possible hypotheses to test. It's not just two, but you could try to hypothesize three things or three truths, right? So it's kind of easy because you just need to compute the probability, the posterior probability of each of the hypotheses, which is reflected by this. This is related with what Jesus mentioned before. So here we are saying that the probability of the parameter belonging to this first set, or this, and then you could choose the hypothesis with maximum probability, right? But this is, we shall discuss about this. This is based on something which is a 0-1 loss, right? And then you can also consider null point hypothesis. So theta equal theta 0 versus. So this is slightly different. Some people say that this type of hypothesis tests do not make sense. In some contexts, it might make sense. For example, to simplify a model, regression model, you would test whether a weight is 0 versus a weight is different to 0. And the approach that we normally use it here is, we will discuss a little bit later on this, but one general approach is we could use an interval with high probability for theta and accept or not. Last, forecasts, making forecasts. So that's what is the probability of what is the number of successes in M future trials. This time I put it in a sort of more adequate notation. So what is the probability of obtaining K successes in M future trials, given that we had these X successes in previous? So that's the sort of computation that we shall be repeating. So should we know the actual value of the parameter, that would be the forecast that we make. That would be the probability that we make. But we don't know this guy, right? The uncertainty that we have about the theta parameter is reflected in this posterior, right? And then what we need to do is sort of get rid of this uncertainty by marginalizing out, by integrating. So and we do the numbers, and also this is a distribution, right? So we can summarize it through the predictive or whatever, etc., right? So this is this type of things is something that sort of traditional machine learning is not very good at. Based on that, I mean, say that we have a predictive distribution. It's not just a pointed distribution, but a predictive distribution, and therefore we can provide much richer information with this, and that's quite important in many, especially in decision contexts. In many decisions, this is quite important. And that was the sort of introduction. So next week, what we'll do is something similar through another important problem, which is means. And for this, we shall introduce the normal model. Yeah. And again, we go back to proportions, but having explanatory variables. So that would be the logistic regression. And if you remember, I mean, the sort of very first joke that we made on the machine learning thing, that was, well, we all do artificial intelligence or machine learning, but in the end, we are many people are actually doing logistic regression. So we'll have a Bayesian version of that thing, which is, so this is machine learning. Okay, and if you have any questions over the week, that's where we are, and the stuff is there already or probably about to be there, right? Any comments or questions? Okay, so we finished.
There's a question next time.
There's a question.
Thanks, bye.
No, bye. He's a very good friend. Okay, so thanks.